Hello everyone, I am Uttam Satpute, Professor Electrical Engineering Department at D.Y. Patel Pratishthan's College of Engineering, Nagar, Kolhapur. Now in this video, we will look at economical load scheduling with transmission loss. So this is very similar to uh, what we have done previously, economical load scheduling without transmission loss. It is very similar, only here we have to consider one term, that is uh, transmission loss. So let us derive the condition. Okay, so what is the criteria for economical load scheduling with transmission loss? That is what we are going to derive. So let us consider that we have uh, a system uh, having n number of power plants. So this is say G1, we have another plant G2, and so on up to Gn. Okay, and these plants, they are connected to a transmission network. Okay, so this is a transmission network we have, and at this point we have a load. So in the previous derivation we didn't have this transmission network. Now we have a load here at this end. Let the load be, now it is PD. Okay, and let the transmission loss be PL, that is, and let these generators, they are generating, let the economical scheduling PG1, PG2, and up to PGN. This is what we are considering a system. So let us write this about this system. Consider a system, consider a power system with n number of power plants, n number of power plants connected to a load, connected to a load. We can take PD through a transmission network, through a transmission network, right, through a transmission network with loss PL, with loss PL as shown. So we can write that it is as shown here. Okay. Now we will now what is our economical load scheduling means what? We want the generations PG1, PG2 and PG3, PGN, such that the total cost of generation is minimum. Let this cost be C1 here, let the cost be C2, let the cost be Cn, and this total cost, that is C1 plus C2 and all, which should be minimum. So that is, now we have to write it analytically. So let us write uh, for economical load scheduling, for economical load scheduling, the total cost of generation, the total fuel cost, you can say the total fuel cost or the cost of generation, the total fuel cost of generation should be minimum. This is the requirement or the objective of our problem, should be minimum. It can be stated as, analytically now we have to state it, it can be stated as, can be stated as C1 plus C2 plus so on up to Cn, the total cost of generation, it should be, we can write here minimum. We can write at beginning that it should be minimum. So in terms of summation, we can write Ci. Ci means now I varies from 1 to n number of plants. And because the cost is a function of generation, so I'm writing in bracket, it is a function of generation, it should be minimum. This is called as, this equation is called as objective function. This is an objective function. So the objective of our optimization, that is this function. This is called as an objective function. Okay. Now we will write a constraint function. Now, but how our generation should be, but the generation should meet the load demand. The generation, I'm writing in short, generation should meet load demand. Meet load. The load plus transmission loss. So you can write both. Now in the previous derivation, what we have derived, so transmission loss. In the previous derivation, that is economical load scheduling, without transmission loss, we have not taken into this transmission loss, but now we have to take it. So it can be stated as, it can be, you can write, it can be written as, analytically now we have to write, that is the total generation. Now I write it in summation, the generation, that is PGI, PG1 plus PG2 up to PGN, from I equal to 1 to n, it should be equal to PD plus PL. Okay, and this PL is normally, we can prove it because the transmission loss depends on the generation. So we can write it as a function of PGI. So it can be, PG1, PG2 and all that. This is an objective function. This is called as constraint function. So this is an constraint function because our generations cannot be uh, anything, but it should be, it should meet the load demand. This is called as constraint. Now, how to solve this optimization problem? We have objective function, we have a constraint function, and in the literature, this can be solved by using a Lagrangian function. So, defining a Lagrangian function, defining a Lagrangian function, so this is uh, Lagrangian function. So what is Lagrangian function? First, you have to write the objective function. What is the objective function? The objective function is summation of our cost, that is Ci, which is a function of PGI, and then plus our constraint function. Now, To write, when you write a constraint function, it should be multiplied by a constant Lagrangian. Uh, this is called as penalty factors, lambda. If you have many constraints, then you can write lambda 1 and lambda 2. But now, because we have only one constraint, so we will write it as lambda. And now we have to write a constraint function. Now, constraint function, I write it as PD plus PL minus summation of PGI. Okay. So, and now, how to find out the criteria for minimum? We want all these generations to be minimum, so we will differentiate and equate to 0. Differentiating and equate to equating to equating to 0. So we'll get it as D. Now we have to differentiate with respect to PGI. So, and when you differentiate this equation, so here we will get differentiation of dci by dpgi plus lambda. Now here differentiation of pd, which is a constant, it will be 0, and because pl is a function of generation, so it will be dpl divided by dpgi and minus, this is 1. We are differentiating with respect to. Okay. So now we got this equation. Now this is to be equal to 0. This equal to 0. So what will we get here now? dci divided by dpgi equal to lambda 1 minus dou pl divided by dou pgi. Okay, now this is what is the criteria. Now this is what the criteria uh, for our economical load scheduling. Now I will write it in more other different forms. Now let this is called as penalty factor. This is called as penalty factor. It's called as penalty factor. Okay, so I will write it in more simplified form. Let Li, this is called as penalty factor, which is equal to 1 divided by 1 minus dou PL divided by dou PGI. Then if you substitute these in the above equation, then we get dCi divided by dPGI equal to, and you will get this here Li this equal to lambda, and this is the criteria what we can use for finding the economical load scheduling with transmission loss. This is called as coordinated equation. Uh, this is this is called this is called as an equal incremental cost criteria. It is also called as coordinate equation, but we can write it like this also: incremental cost criterion with transmission loss. Okay, with transmission loss, with transmission loss. Okay, what it states? It states that the product of penalty factor, the product of the product of penalty factor and incremental cost, incremental cost, incremental cost of all power plants should be should be equal for economical load scheduling. So this is the derivation you have to do if they ask you explain economical load scheduling with transmission loss. Now let us solve one numerical here. This is the numerical which is there in the uh, this is the problem. It is there in the question bank. Uh, okay, so this is the numerical. What I'm taking it is from the question bank. In a system with two plants in a with two plants in a system with two plants, incremental costs are df1 divided by dp1. Now don't get confused. dc1 here instead of using c1 cost, we in our derivation we are using c1 for the cost, but here f1 is used for the cost, so don't get confused it with. So f1 is nothing but the cost only. This is 0.01 pg1 plus 20 rupees per megawatt hour. Okay, then df2 divided by dp2, it is equal to 0.15 pg2 plus 22.5 rupees per megawatt hour. Okay, the system is running under, they say the system is running under optimal scheduling with pg1 equal to pg2, pg1 equal to pg2 equal to 100 megawatt. If they have given one dou PL dou PL divided by dou Pg2 equal to 0.22, then they ask find the penalty factor, find the penalty factor and dou PL divided by dou Pg1. So they have asked these values. Okay, so let us solve this problem. Let us understand what the problem is given here. So now we are using this Okay, so now what they are given, that they have given one system. Okay, so this is generator G1 and there is another generator, only two plants are there and they are connected, and transmission system and then load. Okay, load value what is there, they are not given, but now the system is operating under optimal generation, optimal scheduling, that is PG1 is 100 megawatt and PG2 it is also 100 megawatt, and they have given the incremental costs, that is df1 dc1 by dpg1 and dc2 by dpg2 they are given, and now they have given some values and some values are asked. So we will use this condition, we are going to use this equation. Remember this li d, now instead of ci I use it here fi because they have given it like that. So dpgi equal to lambda. And remember what is Li? Li equal to 1 divided by 1 minus dou PL divided by dou PGI. Okay, now we have given two plants. So we can say I value it is 1 and 2. Okay, now here see here, now they are given dou PL divided by dou PG2. Dou Pg2 means this value I, now they are given this I for the second plant they are given dou PL by dou Pg2. So if they are given these two, we can calculate L2, that is a penalty factor of, so this value they are given 0.22. So the penalty factor we can calculate of plant 2, the penalty factor of plant 2 we can find, that is L2, because I now it is this, so 1 divided by 1 minus dou PL divided by dou PG2. So 1 divided by 1 minus 0.22 they are given. So if you calculate this value, I think this comes out to be 1.2, 1.282. Please verify this answer. Now once L2 is there and already now we will use this equation. Okay, first equation. Okay, for L2 I am using for L2. So also we can write. Now let us first find out this incremental cost for second plant. Okay, then we will substitute. So df2 divided by dpg2. Now this cost it is already given 0.15 Pg2, okay, plus 22.5. Okay, now what you have to do, 0.015 into Pg2. Pg2 they have given, that is 100 megawatt. The second plant is generating 100 megawatt. So 100 plus 22.5. So this comes out to be uh, I don't know the value. Please calculate this value. Okay, otherwise I will calculate. A minute. Okay, so this value it is coming out to be 24. Okay, now let us now what we have to do here, uh, we have to use this equation. Okay, now we have to use this So now we are going to use this equation L2 df2 divided by dpg2 equal to lambda. Now let us calculate lambda because we know L2 as well as this. L2 value already we have calculated. Penalty factor for second plant it is 1.282 into incremental cost for second plant also we calculate 24 equal to lambda. So lambda now we get this value as 30.77 rupees per megawatt hour. Please verify this answer. Now we go for plant 1. Now for plant 1. For plant 1. Okay. For plant 1 now our I will be 1. Okay. So what we can do here. Let us first calculate df1 incremental cost. df1 divided by dpg1. Okay. Now that this they have given the incremental cost 0.01 pg1 plus 20. Now here also we know that our generator plant 1 is generating 100 megawatts, so 0.01 into 100 plus 20. So I think it will be 20 only. Now we calculate L1. Now we will use that criteria. L1 df1 divided by dpg1 equal to lambda. Now in this equation we don't know L1, but we know these two. This also we know, this also we know, so we can calculate L1. So therefore L1 equal to lambda divided by 20. So lambda value it is 30.77 divided by 20. So this L1 value I think it will you will get it as 1.465. 1.465. Please verify. Now once we get this L1, but what is L1? L1 is 1 divided by 1 minus dou PL divided by dou PG1. Now they have asked this parameter. So if you calculate this dou P2, PL divided by dou PG2, PG1, then you will get this value as 0.317. Please verify this answer. Okay, so this is the numerical that is asked in the question bank. Please do this. So in this video, thank you up to this only. Thank you very much.